So good morning, everyone. Welcome to this session on the Gradle roadmap. My name is Adam Murdoch and I'm CTO at Gradle Inc. So as you heard this morning, there's lots of cool things that we've been adding to the Gradle platform or the ecosystem. There's lots of interesting things we want to keep doing to grow those. But in this session, I want to focus on the core of the whole platform, which is the Gradle build system. And in particular, I want to talk about our plans for the next 6 to 12 months in two particular areas, two important areas. So this isn't a comprehensive overview of everything we might possibly do in the next 12 months. This is focusing on these two things. And no guarantees here. This is our intention, but things change. So the first topic, faster builds. So everyone loves faster builds. They're awesome. So when my build is faster, this is central to the whole software delivery process. My build's faster, I can do things more quickly and I can do them more frequently. So I get faster feedback from my developers. I get faster feedback from my CI machines. I get to release more frequently. So this is all good stuff. But I can also scale. So as the build gets faster, I can build bigger and bigger stacks. And I can also be more ambitious with my automation. So as each step gets shorter, I can add more steps to my delivery process. So we've already made some good progress in 2.4, as you saw some nice results before. And our plan is to keep going. So 2.4 good, but not good enough. So our basic plan is to apply these strategies on the left to the things that Gradle does on the right. So these are pretty straightforward strategies. So by cache and reuse, what I mean in particular is reusing inside the daemon in memory. So you might not be aware of this, but the daemon already does this kind of thing now, the Gradle daemon. So for example, we keep task execution history in memory, and we use that across multiple builds in the daemon to make incremental build faster. We do the same sort of thing with dependency metadata. Keep that in memory, use it across multiple builds to make dependency resolution faster. But there are two really important pieces of information on the right-hand side that we don't cache. And we know from experiments and spikes that caching these things and reusing them has a really nice impact on build speed. So the first of those is build configuration. So this is when Gradle takes your build scripts and runs them, applies all your plugins, they define a bunch of tasks, configure them. That's what we call build configuration. That's the model. And so we do all this work at the start of the build, we use that result during the build, then we throw it away at the end. Next time you run that same build, we do all that work again. It's the same for dependency resolution. When you resolve a class path configuration, a class path, for example, we calculate the dependency graph, what all the things should be that are in the graph, what the artifacts are. We use that result, and then we throw that away. Next build, we do the same thing. So the problem is that every time you run the build, the answer to those questions, what does my model, what's my dependency graph, it's almost always the same as last time you ran Gradle. So this is wasted work. Each time we do this, it's wasted time. So we want to be able to cache that stuff. Doing work in parallel, that's pretty straightforward. We don't do those things in parallel. We don't do build configuration in parallel. We don't do dependency resolution in parallel. And we have some task execution. We can run some tasks in parallel, but not all of them. So we want to roll this out so these things, when we don't have an answer cached that we can reuse, when we need to do work, we do that work in parallel so that it's faster. And then by work in the background, what I mean there is taking what we've done for continuous build and use the same sort of strategy for these other things. So we can watch for changes to build.gradle, to your init script, to your gradle.properties file, to wrapper.properties, anything that's an input to your build configuration. We can watch for changes to that. When they change, redo the configuration in the background and have it cached there ready for next time you run Gradle. It's the same sort of thing for dependency resolution. You want to be able to watch for changes in your repository and for local configuration changes. When they change, redo the resolve, have the artifacts and the resolved graph there ready for next time you run Gradle. So this is our strategy for making things faster. We do have one problem though. Well, we have several, but one important one is that our current approach to configuration in Gradle has some serious limitations. And it boils down to two basic problems. So the first is that any build logic in Gradle, so any build script, any init script, any plugin, any event listener, any dependency resolution rule, any task action can query anything. So it can reach out to any project and ask any question, can change anything, and it can do this at any time. So the problem there is then there are implicit dependencies between all these things, but we don't know what they are. So it means we can't reorder things, which means we can't run these things in parallel. The other problem we have is that we don't know all the inputs to this build logic. So we know some of them. So we know that the build script's an input. We know that Gradle.properties is an input. But if my build script reaches out to some configuration file we don't know about, uses some system property we don't know about, hits some web service we don't know about, then we can't cache the result. So we can't cache the build model. And what that also means is that we can't cache, in general, the result of doing dependency resolution. So you think, I have a dependency graph. As soon as I put a project dependency in that graph, then an input to that graph is the configuration of that target project. That's not cacheable, so the dependency result isn't cacheable either. Same thing if you're using dependency resolve rules, substitution rules, component metadata rules. These things we don't know all their inputs to. So we have been working on a new approach to configuration. So this has been in a few releases of Gradle now. This is very much a work in progress still. But if you've been using the native support at all, you will have seen this stuff in action. So I won't go into too much detail here in this session because there are more sessions about the details of this later today. The solution's basically made up of two parts here. First is what we call managed model. So this is a replacement for things like project extensions and the extended properties namespace and things like configuration. So the objects you use now to describe your model, this is a replacement for that, where you describe what your model should look like and Gradle provides an implementation. And so that implementation has some important benefits. So firstly, it's far more efficient than the existing domain objects. So even when you're doing the same amount of work, that work happens more quickly. And secondly, these implementations are fundamentally reusable. So we can reuse these managed objects across multiple instances of the build, multiple invocations of the build. Then we have configuration rules. So this is a way of taking your build scripts and your plugins and applying a bit more structure to them. So breaking them up into smaller pieces, I should say, where we know the inputs and outputs to each piece. So that means that we know what order they need to run in, we know how to run them in parallel. And we can also skip the ones we don't need. If we don't need a particular answer, we don't run the rules that decide what that answer is. So these two pieces address these fundamental problems. It lets us reuse the work we do, and it lets us do the work we have to do in parallel. So we're rolling this out first for configuration for the build model, but later we want to do this for dependency resolution and for tasks as well. So this is a major part of the roadmap for the next 6 to 12 months. Finishing this up, making it stable so that you guys can use it in your builds to see some nice performance improvements. So some results. So these are some results from our benchmarks that we run nightly. These are the numbers from master as of Monday or so. And this experiment is comparing two things. This is taking the existing Java plugin that uses all the existing approaches, all the current domain objects, and comparing it against a new implementation that uses the manage model and the configuration rules. So as you can see, it's quite a bit faster, which is nice. One thing to notice here that's interesting, and is actually what we want to achieve here, is that the build time scales much better with the amount of work that you're asking Gradle to do. So we've got three scenarios here. Gradle help, that's basically Gradle do as little as you possibly can. A clean build of one project out of 500, and a clean build of all the projects. So these first two scenarios, I'm asking Gradle to do a very small amount of stuff. So it's quite quick. The third scenario, I'm asking Gradle to do a large amount of stuff. It takes a bit longer. But what we're aiming for is for build time to be a function of how much work Gradle has to do, not a function of how much work it could do, which is the situation we're in now. And you can see that with the stable plugin. So this manage plugin is it's in master, so you can play with it. Again, it's a work in progress, so it's not quite ready, I think, to use. But part of the roadmap is to finish that up and get it out there for people to use. So so this is pretty good, but we can do better. So one problem we have with the managed plugin at the moment is it's still using a mix of managed and unmanaged objects. That's just because that's where the implementation's at the moment. We're gradually migrating. So we have a second experiment here that mocks up the situation where you have a fully managed using configuration rules plugin versus a fully unmanaged plugin. So this is a mock-up of the Android. This particular experiment is a mock-up of something that looks roughly like the Android plugin. It's very much not the Android plugin, but that's how it's structured. And so here you can see that we have even better numbers. So even the full build is much faster, but the scaling with the amount of work that you need to do is also much nicer. So the first result is where we are now. If you use that new Java plugin, that's the sort of speed up you'll see. That's the sort of performance you'll see. This is where we're aiming to. This kind of thing, which is much nicer. So half a second for that building one variant out of 500, out of 5,000, I should say. So again, this is only applying these strategies to and this new infrastructure to configuration. This doesn't include applying those to dependency management and to tasks. So we expect to see it even better results once we get to that point. So this is all very exciting. So our second topic that I want to cover today is dependency management. So build time, making builds faster is about scaling with the size of things. Dependency management is all about scaling with complexity. They're often correlated, but not the same thing. So this isn't probably the association you'd make when I say dependency management. Dependency management has been really, it's quite a complex, it appears to be quite complex, it appears to be flaky, incomprehensible. This doesn't have to be the case. So we want to make this to not be the case. So dependency management is all about exposing the dependencies, the relationships between pieces of your software, the relationships between your teams and how they collaborate, and the relationships between the various stages of your software delivery process. Taking those, making them explicit and applying automation to them, visualization to them, and tooling. So what does that mean? So there's a few specific things we want to do here. So firstly, we want Gradle to be a true cross-platform build system. So that means we have to be able to build all kinds of software. That means we need dependency management that makes sense and that works for all those different kinds of software. When you're building a Java library, We want you to have dependency management that makes sense for Java libraries. When you're building a native application, we want dependency management that makes sense for native applications. When you're building your own kind of software that doesn't exist anywhere else, we want you to be able to tell us about that and define dependency management that makes sense for that kind of software, and then have Gradle implement that for you. So we've been working on something we call the software model or the component model. Again, there's more sessions about this later today, I think. So I won't go into too much detail here. Again, this is available in master. If you've been using the native support, you will have seen this in action. And a major part of the roadmap is rolling this out so it's available for everyone. As far as dependency management is concerned, there are two important concepts that we've introduced in the software model. So the software model is a rich description of what you're building. So it's not just apply plugin Java, it's I'm building a Java library, I'm building a Java application, I'm building a native executable, I'm building a web application composed from this JavaScript library and these static assets and this JEE component. So platform is all about where does my software run? Do I intend it to run on Java 9 or later? Do I intend it to run on Java 6 or later? Do I intend to run it on Windows? Which versions of Windows? Which versions of Android am I targeting? What kind of devices? Am I running this code in Node? Am I running it in the browser? These are all examples of platform. So this is something you describe in the software model. Gradle uses that in order to build your software. And then that information doesn't yet, travel with your artifacts as metadata when those things are published. Then we can use that to do dependency resolution. We can take into account the description of where you want the software to work. So if I'm resolving dependencies, I'm building for Java 8 and I'm resolving dependencies, I depend on a library that says it works on Java 6 or later, cool, we can use it. If another one of my dependencies says I need Java 9 or later, then we have to fail. Sorry, we can't satisfy your requirements. So, platform, what am I building? Where does it run? Bake that into dependency resolution. So we want this to be extensible as well. So we want you to be able to describe the types of software you're building, but also to add new kinds of platforms on which they can run. Tell us about them. Dependency resolution can honor that. So the second important concept here is what we call variant, or variants. This captures the common pattern, it's everywhere, where for a given piece of software, you need to produce multiple different outputs for different purposes. So using that for platform is a classic example. I've got a native application, I want it to run on Windows and OS X. I can't build a single binary, a single output that runs on both those platforms. I have to have two different binaries. So you tell Gradle, here are my variants, here are the different outputs I want to produce for this thing. We can build those things. But then we also want that to be baked in to dependency resolution. So again, the metadata travels with those artifacts as they're published, and dependency resolution can take that into account. When I'm building my Windows variant of my application, I need to choose the Windows variant of my libraries that I depend on. And if a library doesn't have a Windows variant, I need to fail. We can't build that application. So again, we want this is open. You can define your own variants for each of the things you build, pieces of software that you're building, but also new types of variants as well. So combining these pieces, defining what type of software you're building, the platform that it runs on, the variants that it can have, and compatibility rules between those things. Using that toolkit, you can define dependency management that starts to make sense for the type of software that you're building. So here's a concrete example, or hopefully somewhat concrete. So one place where we want to use this capability is for good Java 9 support. So Java 9 introduces a module system. There's a new format, a new output format for modules called JMod. There's an interesting new output format called a runtime image, which is where you take, if you're building a Java application, you can package up your application, the modules of your dependencies, and the modules of the JVM that you need into a single executable. It's all optimized, it's all linked, pre-linked, nice and fast. So that's pretty cool. So we want to be able to, obviously, or clearly, we want to be able to build these new kinds of outputs. When you say, I'm building a Java library and it runs on Java 9, we want to be able to produce JMod outputs. When you say, I'm building a Java application and it runs on Java 9, we want to be able to produce the runtime image. So this has some interesting implications on dependency management. This is really the first time, it's not actually the first time, but this is when concepts like platform and variants become important in the JVM domain. So far we've just sort of worked around these things and pretended these problems haven't existed, but this makes it very much apparent. So if I'm building for Java 9 and I want to produce JMod outputs, when I'm resolving my dependencies, I need to choose the JMod variants of the things I depend on. But if a dependency doesn't have a JMod output, I can choose the jar. I can fall back to the jar output instead. When I'm building for Java 8, I can't do that. I have to choose the jar variant, and if there isn't one, I need to blow up. So the concept of variants becomes really useful, I think, for Java library authors. So what they'll be able to do is to say to Gradle, please produce a Java 9 JMod variant of my library and a jar variant for people who are still on Java 8 and haven't migrated, or who are on Java 9 and aren't using modules yet. So this is really interesting migration story there using variants. And variants can be used for all kinds of interesting things. I produce a jar, I produce a shaded jar. I want to produce a minified JavaScript library and a developer JavaScript library. I want to produce a web application targeted for that environment or targeted for that environment. I want to have a test suite, a functional test suite with 3 variants. I want the first variant, same test, to run against my application and the versions of my dependencies that are in QA. I want a second variant of my test suite, same test, run against my application and the versions of my dependencies from production. Same test suite, another variant, test my application against the versions of my dependencies that are in master. So something else that Java 9 makes explicit is the distinction between the API of something and the implementation of something, of that thing. So we want this to be a general concept here. We want to make this explicit and strong. So for any type of library, when you're building against that library, you need the API of that library and the dependencies of the API. When you're running against that library, you need the implementation of that library and the dependencies of the implementation. So we also want dependency management to mean something more than download my library. We want it to mean dependency management. So a build has more dependencies than just libraries. And there's 2 we want to capture. So the first is what we call build platform, which is the platform in which the build runs. So that's things like the JVM that you're running on, which version of Gradle, which plugins, which versions. So you can do this in a somewhat ad hoc way now. We want to make this a bit more formalized, make it an actual dependency of the build. We also want to capture tool chains, the tools that the build uses to do its work. So these are things like Java compiler, the C compiler, source code generators, linkers, bundlers that produce binaries, things like that. So these are dependencies of the build. They're things that the build requires. So we want you to be able to define them, different tool chains, and declare dependencies on particular versions of the tool chains. So I want to be able to say I need GCC 4.6, or I need protobuf 2.4, or whatever. You declare that in your build, and then Gradle goes and resolves those things, finds them, and makes them available to the tasks in your build. So resolve here means something slightly different to resolving libraries. And there's two strategies we want Gradle to be able to provide. So the first is, for those tool chains where it's possible, you should go up to some binary repository, download the tool chain, install it, and then reuse that installation for subsequent builds. And for those tool chains where that isn't possible, we want Gradle to be able to inspect the build machine, find the installed tool chains, and choose the right version, or fail with a nice error message when it can't find one. So we've taken the discovery approach in the native support. You declare which tool chains you need, and it goes and finds Visual Studio or GCC or Clang or whatever. So this is already there in the native stuff. So I want this to be a general concept here. So these things have some really nice benefits. So there's a really nice provisioning story here, or onboarding story. My dependencies are in my source. So if I check out my source and do Gradle blah, Gradle can go and find all the things that the build needs. Not just the libraries that the build needs, but the tools that the build needs as well. So as a developer, I just come along, check out some source, off I go. I don't need to set up my machine with all these things. Same for a build machine. Point build agent at source, everything just works. Import source into IDE, everything's there. So there's a really cool repeatability story here as well. So again, everything's described in source. So if I check out the same revision in two different places, I get the same result. So two developers, same revision, same result. Two build agents, same revision, same result. Developer, build machine, same result. And then there's repeatability as well. So what we can do is, this is all declared in the build. Gradle knows about these things, so we can capture them in a build receipt. So we can go, however it came about, here's the version of Java that the build ran in and where it came from. Here's the version of Gradle that the build ran in and where it came from. Here are all the different tool chains it used and where they came from. Here are all the libraries we built against. Here are all the plugins we applied. Here's all the test suites we ran. And here's all the dependencies, the inputs that those tests use. We can capture all those things, their versions, and their origin. They can go up in the build receipt. So there's some really powerful diagnostics there. You can share this information. Some really cool analytics you can do. You do that across multiple builds. And what you've also done here is you've essentially captured the whole build environment. So you've captured all the information about all the inputs that affected the build. So that means you'll be able to repeat historical builds. So I need to wind it up now. So we'll leave the roadmap there. There's a lot more stuff we want to do, a lot more stuff in dependency management and other areas. I'll open it up to questions now. Is there any questions? Yes.
I'll talk a little bit about distributed cache coming later. Can you speak at a more high level, like what your approach would be to distributed cache and what your goals are there?
So the goal is to take what we know about the inputs and outputs of a task and use that information to distribute the work. And then there's two aspects to this. So basically a task is a function that takes some inputs and produces some outputs. So what we want to do is we know, and almost most tasks, once you capture all the inputs, they're deterministic. So they'll produce the same result, or they'll produce approximately good enough, close enough of the same result that you can reuse the output from a task that ran somewhere else. So what the global cache to answer is, when I'm running this task with these inputs, has someone else or something else already done that work? If so, grab the outputs, pop them down on the local machine or wherever you're doing the build, and it's done. You can short circuit the work. So that's distributed cache. And then distributed build is basically using the inputs and outputs to schedule the work on different machines, pop that information into the global cache, and then move the artifacts back. Oh, sorry.
You said that the improved configuration schema will find changes in the remote repositories. How will it be done?
The same way we find changes now. So it can be an approximation. So you think like the caching that we do now, we check once a day, you can tweak that. So we'd probably do a similar kind of thing. So what we want is a description somewhere about a particular module, about how variable is it, how frequently we should check for changes. And then we should apply that everywhere that we do caching for that thing. So we would take that information and apply it to the local cache, but we can also take that information and apply it to check for changes. Ideally, because we're using the daemon, we can do this a bit more frequently than we do now with when we're doing it inline in the build. So we can tweak that up. It'd be lovely if we could get stuff being pushed out. And this is where the global cache can be really interesting as well. So if there's a cache, when you're publishing, that's a task. It produces some output. So if we can push that information around, we can get that down to the daemon. The daemon can know that something's changed and can go and fetch it. So initially, just dumb polling, but later, once we get further down the roadmap, it can get a lot smarter. Yeah.
Is there anything that you can summarize for the roadmap where those will get some attention and sort of polish that?
Yeah, so there are two things there, I think. So the first is something that's pretty fundamental to the managed model is this idea of reusing existing things in new places. So creating new source sets and creating things like new types of reports. Once that concept is in the managed model, you'll be able to extend it extremely easily, and you'll be able to take any part of your model and say, please put a report in there. And not just an arbitrary report, my report, pop it in there. Same with source sets. So that's the first part of the answer, is that this actually does cover those kind of pains, but it's definitely a longer term solution. In the short term, there's a lot of other things that we do as we're developing this stuff. So each Gradle release has, it's not just big stuff, there's small stuff mixed in there as well. So we need to work on our prioritization to get the right sort of usability fixes in there for existing stuff. We don't want to ignore the existing stuff. We don't want to go, we're only doing new stuff, it's going to be awesome, but wait, it's going to be great. So yeah, finding that balance is a bit tricky. We're working on that, but that's definitely our intention, is to keep progressing the existing stuff. And something I should say as well is that these things have been running together. The legacy stuff, or the stable stuff, and the new stuff have been working together in Gradle for quite a few releases now. So we can bridge tasks from the old model to the new model. We'll be able to bridge other types. So this isn't a big bang thing at all. So the intention is that there'll be a nice migration strategy, a piece at a time, across to this new world. Maybe a pane-driven sort of strategy there. Most pane, move it across, gradually clean up. Yeah.
With the move to these tool chain dependencies and declaring them, there's a lot of overlap between like what the Gradle wrapper does
Yes.
and these tool chains.
Yes.
Is there going to be a day, or is it on the roadmap to get build the Gradle wrapper functionality directly into Gradle?
Yes. Yes. Absolutely. That's where we want to get to. Is we want to basically unify this stuff. So there's a few different places that you. So this is all part of the build platform. So and currently the build platform's kind of scattered through a bunch of different places. We want to have a single place where you can define these build platforms and define which build platform your build runs on. And then that implies things like where the wrapper should get your distribution from, where your plugins should come from, which default versions of your plugins should be available, which plugins should be automatically applied, that kind of thing. And from that, then you can build things like where are my repositories and where's my infrastructure. So the answers are yes.
So I'm interested in how the variants play a role in dependency management. Like what kind of metadata that is or will be used to describe those variants. Like for,
Yep. So there's two classes of metadata here, or stuff that interesting attributes of the variant. So there are attributes that are sort of fundamental to the domain or the type of software that variant's for. So for Java libraries, it would be which Java platform it should run on. For native executables, it'll be things like which operating system, which architecture, which ABI, things like that. So those will be baked into the models for those kinds of binaries. But we also want this to be extensible so that you can define whatever attributes make sense for whatever it is you're building. So you can define new attributes for each variant and give them a type, and then that will be encoded in the metadata that gets published. But also the metadata is used locally as well. So when you resolve a project dependency, you're using the metadata. It just doesn't turn into a pom.xml or an ivy.xml, but it is being used there. So it'll be used for those two cases. So so some rich metadata, some of it predefined, and kind of stuff that makes sense for that domain, and then whatever other stuff you want to define on top of that, basically. We don't know the full set of the universe of variant attributes, but collectively we all do.
So along the metadata lines, you've been working on the native features for a while now.
Mm-hmm.
If you look at Java, it has lots of metadata, almost not always great. The native one doesn't. When are you thinking of starting to publish metadata? What sort of formats, based on your experience, you're thinking about publishing?
Good question. Part of rolling out the software model has to include publishing the software model. So in the next sort of in this time frame, so the next 6 to 12 months, definitely. Because basically the software model isn't usable until you can publish the artifacts and the metadata. It lets you build things. That's fine. That's kind of nice. But that's really that's not the big story here. This is about being able to take these things and arrange them in all kinds of interesting arrangements. And you need to publish the metadata in order to do that. So it's a fundamental part of finishing this up. And finishing this up is a fundamental part of this roadmap. So soon, hopefully. There's a bunch of us have got long haul flights coming up on the way home. So maybe, who knows? So, any more questions? Yes.
I change the syntax in my Gradle build, or I need some moments of and then I went to one of my notes that was behind firewalls.
Yes.
So, this is gives me an opportunity to ask, is that going to be fixed? Is it something that we specify where it's going to present?
Yeah, so there's a few aspects to this. So is this going to be fixed? Yes, we definitely have to solve that use case for plugins, definitely, and for libraries, for my libraries that I'm building in my organization, definitely, absolutely, that just can't work if I have to go out to the world and say, oh, I'm going to share all my libraries with everyone, anyone can see them, that kind of stuff. So definitely need to fix that use case for plugins. So the idea here is that there's a difference between what the model is and where the model lives. So for Gradle to do its work, it just needs to know what the model is. It doesn't actually care where it comes from. So the idea is to have a bunch of mappings from various different locations or different ways of storing different repositories that the metadata can live in. Turn that into the Gradle model internally in Gradle and then do the resolve. And so there's a few locations where we definitely need to support. So the first is in the DSL. That's a source of metadata. So for the stuff I'm building, we'll use the DSL and the local model for defining that. Your existing Maven and Ivy repositories have to keep working. So there needs to be some bridging, definitely, from those types of repositories into the model and from the model back out to those types of repositories. So that's what we're aiming for at the moment, is local dependencies and things that have been pre-built on the local machine, stuff in Maven repositories and stuff in Ivy repositories. So there definitely won't be the same sort of step back, if you like, that we saw with plugins. So want to fix the plugins use case, and we definitely need to be able to use your existing infrastructure and whatever topology makes sense for whatever it is you're doing for doing dependency management. So we're pretty much out of time now, so thank you everyone.